First, okay. Started the recording, so I'm not gonna forget. Thanks for those of you who have sent the introduction of yourself on the forum. I'm really enjoying reading your introductions. Let me share my screen here. Several things on the screen. Yeah, today, as I told you today, we're just going to do an introduction of how to approach science in general. I will approach science, I will approach biology. So it's a pretty straightforward lecture. I'm sure that either you are being off the high school 5 years ago or 10 years ago, you will probably recognize some of these things that you have probably learned in high school already, or how to approach science and a scientific process in general. Okay, that's what we're talking about today. And then we're going to talk about a few examples, how we can apply this process even to very biological questions that sometimes you don't think that there's anything you can do to answer a biological question with a scientific process approach, but there's always a way. You have to be very creative when you deal with science. All right, so let's see, it's 1:02, it's 9:02, and I think I'm gonna go ahead and start. So I'm going in presentation mode. When I am in presentation mode, I'm not able to see if you guys type questions for me. So if you don't mind, if you have a question, feel free to interrupt and ask it, speak it. Because typically I hear a beep and I'm like, what's this beep? So I have to go out of presentation mode and to read it. Sometimes that back and forth creates problems. Sometimes I make mistakes. I click something wrong and I have terminated my presentation. I've done weird things. So the less I do that, the better, in other words. All right. So as I told you, today we're going to look at the scientific process, the way we approach science nowadays. That has not always been this way. There were times in the past where science was not approached in this way, and there was a lot of contamination from religion, personal beliefs, all these things. We'll see how we take them. We try to take them out of the picture as much as we can nowadays. So we're going to describe the scientific process and the systematic steps. So it's a logical process, really. You could even possibly come up with it. You don't have to memorize it. If you think about it, it makes a lot of sense. That are typically applied in the scientific process. Then we're going to define what is an hypothesis, what is a theory. These are two different things, okay? This is something I would like you to remember well for me. And therefore recognize what are the differences between an hypothesis and a theory. And then we're gonna give examples of how the scientific process is properly applied in certain situations. Okay, that's all. So before we start, I just want to give some definitions. Of course, here this is a biology class. Biology is the branch of science that is dedicated to the study of life. Bios from Greek means life, okay? So biology, study of life, and of course there are many questions that we can ask from things like that. Again, it seems like we can't really apply the scientific process maybe to questions like this. How do living things interact in communities? In reality, we can always apply the scientific process, and I'll give you examples of what you can do. Is that a question? I heard a beep. Did anybody ask a question?
No, it might have been me being logging in because I had to kind of go out and come back in. So that's probably what it was.
All right. Okay, and so biology is a branch of science. So science actually from Latin means to know. So really in science we want to know the truth, okay? And in order to know the truth, we have to apply a scientific inquiry process, which is this is a problem-solving method, and it is objective. And the word objective has a specific meaning here, which I'm going to tell you in a minute, okay? So scientific inquiry is a problem-solving method. As I told you, it's something, I'll give you examples. You apply this method every day in your everyday life because it's a logical process. So there is nothing really here so difficult to remember or understand it, because it's a natural process that your mind uses every day, because you're every day faced with questions or problems that you have to solve. And so when we talk about scientific inquiry, this is used to study phenomena that can be observed and measured. I want you to really pay attention to this word here. If I cannot measure something somehow, then I cannot scientifically prove a certain phenomenon, okay? In other words, if I cannot come up with numbers that answer a question, then I cannot answer that question, because the only objective thing in this world are numbers, okay? And I will talk about this a little bit more, okay? So if I can't measure, I can't come up with numbers, I can't prove my point, okay? And so I can only apply scientific inquiry to phenomena that can be observed and measured objectively. And objective means also that the methodology that I use is not biased or influenced by personal beliefs, feelings, opinions. When I set up a process to prove a certain phenomenon, I have to try to use unbiased approach, right? Because if I already bias my approach to try to push the results towards a certain outcome that it matches my beliefs, that is highly biased, right? I cannot do that. We don't do that nowadays. People used to do that, right? In the past, medieval times, and scientists have been coerced, have been even exiliated because they were saying things that were against what was written in the Bible. So, science was very much influenced by religion, by personal beliefs in the past. And we know this doesn't happen anymore, okay? Because we apply the scientific inquiry very, very rigorously nowadays. And so, of course, every scientist is also a human being, right? So I guarantee you there is always a little bit of bias, even when, the highly respected scientists, sometimes they don't want to believe data that they have in front of them just because the data don't match with maybe what has been published before. There is a little bit of scare there to say something that goes against what has been published. This has happened to me, when I was in the research. I remember presenting my data to my principal investigator, and my data were in contrast with what was published in the literature, and he was telling me I was doing something wrong, this cannot be. And sure enough, after years of study, and finally we were able to publish what my data was saying. And sure enough, after my publication, a number of publications came out in line with mine. So, just to tell you that sometimes we are still biased, because we're still human beings. But obviously, we apply the scientific inquiry process to our to our investigation, no matter what. Now, there are things in this world that we can observe, we can have opinions about, but we cannot measure. And if we cannot measure, then we cannot prove our point. For instance, let's try to answer this question. Which painting is better? Raise your hand if you think that the one on the left is better. Wow, many people. So the fact that many of you like the one on the left, does it prove the point that the one on the left is actually better? Let me go in out of presentation mode. I want to see what you guys are saying. It is bias. Let's see. You guys are saying no, no, no. No, I agree with you. No, because this is a type of question where I can't measure. What I can measure, though, is how many more people like the one on the left versus the one on the right. That I can measure, right? But does that prove the point? Does that answer that question? It doesn't. It just tells me how many more people like one versus the other. So I collect statistics, but it does not tell me the answer to this question, right? Because I can't measure which one is better. It's not a measurable type of question, right? Let's try to ask a different question now. Okay, we all agree. Very good. Oops. Let's. Ooh, what's going on? Which painting has a thicker paint? Is this a measurable type of question?
Yes, ma'am.
It is, absolutely. Yes. There are methodologies that I could use. There are instruments that I could use to detect which painting has the thicker paint. So it's definitely measurable. I could come up with numbers. Okay, there it is. If I can come up with numbers, then numbers tell me an objective answer to this question. So numbers, remember, are the only objective thing in this world. There is no other thing that you can rely on in order to know the truth about an answer to a question. Now, let me ask you another question here. All right, I have an instrument. It's known as spectrophotometer. Maybe I can run the spectrophotometer right in the middle. Oh, you don't see my pointer. Let me go in presentation mode. Like in presentation mode. And so I go ahead and take this point over here and this point over here in the middle of the two canvases. And I run this instrument, and this instrument says that, this painting has I don't know, 0.2 millimeters. Sorry, my handwriting with the mouse is horrible. This one is 0.1 millimeters. Okay, do I have my answer?
Yes, you do.
Let's talk about this. Let me go back out of presentation mode. All right, so does everybody agree that just doing one measurement in the middle of the canvas would tell me an answer? Why no? Drew, AJ, am I saying it right, your name? AJ?
Yeah, that's fine. So I mean, no, you can't just take one point and figure it out. There's just one point. You need a lot more data to basically create a hypothesis, or basically a lot more data to create an average of how much thickness of paint was used.
I totally agree with you. Okay. That would be the logical thing to do, because I could be very biased just to choose one point. So, for instance, one good thing would be to maybe to put a grid, the same grid that has many points, along all the area of one canvas versus another, because obviously, the painter may have used put a little bit more paint on some areas and less on another. So I need to get a much bigger number of data and average them out. I really like that. Okay, I really like your approach, and that's the right approach. Okay, lots of data, not just one. So for instance, I create a vaccine, I tested on one person, it works, and I say, oh, this vaccine works, right? It doesn't work that way. You have to have much more data in your hands. Okay, so we're going to talk about more really examples that apply to real life and even drugs, or that the drugs are tested. All right, and then I have one more question, but I'm not gonna answer this question until later on. Okay, I just want you to start thinking. All right, let's go back to our data. That now we know that, for instance, we can create a grid. Okay. And take points. For instance, I create a grid this way, lines that go this way. I'm not going to finish it line that goes this way. And then I take all these points. I measure 1 point here, 1 point here, the grid. And I apply the same grid to both canvases. So now, let's go back to our results. I average out all my points from one canvas and the other, and let's pretend that I get again 0.1 millimeter here and 0.2 millimeter here. Do you think that I can say for sure that this canvas has a thicker paint than the other? And I shall say what we also need to do, we need to create a control. We'll talk about controls. Imagine that we have done everything properly. For instance, this canvas itself could be thicker, the actual canvas, than this one. So we have to make sure that we zero out that we measure only the paint. Let's say we have done that all correctly. Okay. And let's say that our numbers, our averages are this. We have taken, say, 100 points from one canvas, 100 points from another. I think it would be enough, right?
Well, I don't think you can, because you're not taking in the whole painting. You're only taking half the painting. So it's a hypothesis.
Sorry. I just didn't draw everything, but just imagine I told you. No, it's horrible the way I
was like, oh, she only did half the paint. No. But yeah, if we're only zeroing out the amount of paint that was used, yeah, I would say so.
So we're gonna talk about this. Again, this is just an opinion, because yes, even if I get a higher number from one canvas versus another, I still am applying an opinion to these results. There must be some objective procedure that I can use to really prove that this number is really higher than this one, in the sense that, yeah, of course it is higher, but that the fact that I got a higher number for this canvas, it's not just a result that I got by pure chance. Okay, and we'll talk about this in a little bit here. There is no way you can publish some results like this in Science just because you have gotten more people responding to a drug versus a placebo, and you have those numbers. If you don't take a step forward and prove that that difference is real in some way, you're still not. You still can't say that that drug is really effective. Okay, I'm gonna talk about this in a little bit. Okay, as I told you, I was gonna ask the question to leave you, thinking. I'm gonna answer the question. That I'm gonna tell you what we do in a little bit. Right now, I want to talk about the scientific method. Now that we have approached the question and try to, and we have understood that we need to conduct an experiment. Our experiment in terms of Canvas was to create a grid and to set up a system that was unbiased for both, to measure thickness for both canvases. So we have done our experiment, right? So there's an experimental procedure that you set up whenever you ask a question and you state an hypothesis. For instance, our hypothesis initially could have been that it really looks like this one, as first approach. You look at the two canvases and it seems like this one on the right is the thicker one. But we could be highly wrong because maybe different types of paints, maybe this is an oil-based paint that looks where the colors look more intense versus a water-based paint. So when we make an hypothesis, when we formulate an hypothesis, we could be completely wrong. Typically, scientists, they formulate hypotheses based on just preliminary data or just very preliminary observation. And I'll tell you what, 99% of the times when you formulate an hypothesis, that hypothesis is wrong, because it seems like it's always the case. The many years that I've been in research, that was always the case. There were people working on projects to prove a point. Myself, I was working on a molecule that my principal investigator said, this molecule is an activator of genes. And guess what I published? It's a repressor of genes. So it's the opposite, right? So you state an hypothesis, you have to be very open to change your hypothesis. And many times your hypothesis is actually opposite to the reality. So you state an hypothesis, you conduct your experiment, you set up your experimental procedure where you control everything. We'll talk about controls more in a minute. And then you gather your data. Our data in the example of the canvas was just the numbers, the thickness that the instrument would detect for us. We would put this data together, average them out, and analyze the results. Okay, this is where you have to understand there is an extra step that you have to do. Averaging out your data, representing them on a graph is not enough to prove a point. There is something else that you have to do to your data to prove that your results are not just have not just been obtained by pure chance. Okay, and I'll tell you what exactly you do. So after you have analyzed your data, the analysis of your data, and I'm going to add another word now, the statistical analysis of your data is going to tell you the truth. And you can make a conclusion. This conclusion can be validating your hypothesis or can be rejecting your hypothesis. Okay? So either you prove your hypothesis or you just have to reject it. Okay? And if you reject your hypothesis, you have to make a new one and set up another experimental procedure to maybe, again, prove a new hypothesis, okay? And so that's how scientific method works. Sounds complicated? Shouldn't be, because you use this process every day. Every day you're faced with problems and with surprises in your life, right? And you have to find a solution. For instance, this is an example that's in your study guide, so I put it here. You go to your car after class and it doesn't start. What's the first thing you think? Now, your initial hypothesis also depends on your surrounding. If you live in a city where there is a lot of crime, where people even steal batteries, your first thinking may be, oh, they've stolen my battery. But if you are in Austin, it's pretty low crime, right? You wouldn't think that. I'll tell you, I come from south of Italy, where from a city that probably has the highest crime in Italy, crime rate. And yeah, maybe the first thinking, maybe for me, if I were there, for a student there, I would be that, you know? And so, and anyways, you think the first thought would be some problem related to the battery. But if you are a student that tends to forget to put gas in your car, it may be also, oh, I ran out of gas. And see, even the fact that you're, if you have an old car, you know, it happened to friends of mine that their indicator of gas level was broken. So they pretty much, they had run out of gas, but they didn't know it. And they couldn't tell because that thing that indicates the gas level, it was fine. And so it took them a long time to figure out that that was the problem, right? But they went like step after step and tested the battery and other things, and then finally realized that that was the problem, okay? So you formulate hypotheses, and of course, if you're thinking about batteries stolen, you can look still there, right? And if it's still there, so it's not stolen, maybe it's dead. And again, there are ways to predict or to test if the battery is dead, because you can test your lights and other electrical things in your car. And so you apply a problem-solving method, right, to answer this question. And it's something that it's the same thing that you do when you apply scientific inquiry. So it's a logical process, okay, that you apply every day in your life. There's nothing else than that. And the scientific process uses inductive and deductive reasoning. Inductive reasoning refers to the ability to create an hypothesis, to putting together facts that maybe are disconnected from one another, so putting them together in a cohesive manner to formulate an hypothesis. For instance, this is an inductive type of reasoning. But then once you formulate that hypothesis, that stepwise process that I showed you a couple of slides back is a deductive reason, is a top-down logic that uses the if-then. So if this thing happens, so when you formulate, when you build up your experimental procedure, that's the kind of reasoning that you're using, okay? And so in a way, science can be considered a process of elimination. And many times, I told you 99% of the time, your hypothesis is wrong in science. And so you have to keep eliminating it, and then you formulate another one. It may be also wrong, proven wrong by your data. And so sometimes you really are left with no other hypothesis to make. You know, it happens. And so you also have to keep in mind that hypotheses can be that are proven right today, they may be proven wrong later on by somebody else. And what happens here is that the longer an hypothesis stands without being rejected or proven wrong, the more this hypothesis goes towards becoming a theory, which is something bigger than hypothesis. So here I want you to pay attention to these definitions. An hypothesis is a tentative statement to explain a phenomenon, and is derived from very limited evidence. Sometimes you don't even have any preliminary data to formulate an hypothesis. You just base your hypothesis on literature that has been published that may be about things that are similar to your case, you know. So that's when you put all this, you know, when you use inductive reasoning. Okay, so you put together other knowledge, pieces of evidence, or very limited data, and you formulate an hypothesis, which is really a tentative statement here to explain a phenomenon. And of course, your hypothesis has to be subject to testing and experimentation in order to be proven through the scientific process. Okay. And when you test an hypothesis, as I was trying to just introduce to you before, you have to always control your experimental procedure. In the example of the canvases, you want to zero out the thickness of the actual canvas because you want to know which paint has thicker paint. But it's possible that the canvases have different thickness. So if you don't control your experiment by eliminating that, subtracting that difference in a canvas thickness, you can be very mistaken. Is that right? So you have to control your experiment. Every experimental procedure is going to have a control. And of course, the control, you have to figure out what a good control is many times. Many times you use different controls. I'm going to show you a graph from an experiment that saved my life when I was doing this intense research in my PhD. I didn't use one control. I didn't use two controls. I used 3 control groups. Just because the more control you use, the more believable you are, okay? And the one other thing that is important to understand is that whenever you are testing an hypothesis or a phenomenon, you can only look at one variable at a time. If you look at 2 or 3 variables at a time, there's no way you can have a straight answer. I'll give you examples of this. And when we talk about variables in an experiment, so you set up your independent variable, which is the factor that is being tested. For instance, the thickness of the canvas, okay? Say if I wanted to test at the same time the thickness of the canvas and what else could I test there that gives me number? Any ideas? For the canvases, what could I test? Can't think about anything else that I can test. Any ideas? The brightness. Yes, well, go ahead.
Type of canvas used, wood frame, metal frame. What else? What the type of paints used as well?
Type of paint, maybe the brightness of the intensity of the color of the. Yeah, something that I could measure. But if I were to do it together, these 2 variables measured together, I couldn't figure out.
No, because that's from them. You're comparing apples and oranges, right? Versus like figure out the common denominator and not the sliders.
Okay, we all agree on that one, I hope. So there is only one variable at a time, one factor that you can test at one time to get a straight answer on your question. And so that's the independent variable, is the factor that you're testing. The dependent variable is the factor that is being measured. It's your data, basically. It's dependent from what you're measuring, right? That's why it's called dependent variables, your numbers, okay? All right, so let's give a real world example of an hypothesis, in scientific hypothesis that you're testing. For instance, you're testing a new cancer drug. I should change this one with a vaccine, right? Nowadays, we're talking about vaccine, right? So they have done testing, right, before putting this COVID vaccine out, and they have followed this exact procedure, no matter what it is, okay? So you're testing a new drug or a new vaccine, and that's your independent variable. You can only test one at a time. If you are mixing different vaccines together in a study, you're not going to get a straight answer. You're going to know which one is being effective, right? So there is no way you could use more than one independent variable. You understand that, right? And so in this example, we are testing a cancer drug, but it doesn't matter what it is. It could be a weight loss drug, okay? Or it could be a vaccine. It doesn't matter. The approach is always the same. So your independent variable is that drug, of course, or that vaccine. And your dependent variable is the effect, okay, that this drug has on the tumors in this case, or on the weight loss, or on the ability to not be affected by a virus or a bacterium if you're talking about a vaccine. And the underlying assumption in an experiment like this is that the independent variable is causing a measurable change in the dependent variable. There is no way I can say that a drug or a vaccine is effective if I don't collect numbers. Again, measurable, I have to get numbers. And I have to control my experiment. How do I control my experiment here? What is my control in this type of experiment? So imagine I just take a drug, say let's talk about weight loss drug, okay? Because cancer drug is more like difficult probably to understand. Let's say I take this drug and I give to a group of people. This group of people happen to lose on average some weight. And I go ahead and I tell the FDA that I created a good, or I tell the population that I have this miracle weight loss drug. Am I going to be true? What am I missing here? Any ideas? Can I just take this drug, give to a group of people, and say, and then measure, take numbers, measure their weight after a while, and on average, maybe there been a loss of 5 pounds in 3 months on this group of people, and I say that, yes, my drug, let's see, I'm having responses, but I can see them. Let me see. I say, so there are students that are saying no. AJ, Martin, no. I agree with you, but why not?
Because you would have to measure their exercise that they've been doing, if they were all doing the same exercise, what they were eating, if there was any like other illness that might have caused a weight loss.
That
I mean, there's a bunch of other stuff that you have to do.
That is very true. But I want you to think about it more. I just take the drug and I test one group of people with a drug, assuming that, let's say, assuming that everybody maintains the same rate of exercising, and a mixed population, maybe all kind of gender, I mean 50-50, and age groups and things like that. I mix it really well so that there isn't that bias towards maybe younger people, you know, that exercise more, lose more weight and things like that. Everything is controlled within this group. But what am I missing? Rachel, you're close to. Rachel, says, do you need an experimental group and one control?
Yeah,
That's
so like a
the key.
placebo group?
Very good.
Okay.
If you don't do that, nobody is going to believe you, okay? Because without a control, you can't report your data against a zero, okay? And therefore, what are you comparing it to? You don't have a comparison, and you can't even run your statistical analysis, which is key to accepting results or data as true, as I will show you, okay? So very good. Now, we definitely need a control group. And this control group, as you said, is going to be a placebo. And so there is going to be my experimental group, which is the group that receives the independent variable, which is the drug, right? It never changes, is one. And a control group, which is very similar to, it must be very similar to my experimental group. For instance, if my experimental group is a group of people of all ranges of age, so I have 100 people, and I have like 5 ranges, like 20 people are between 15 and 30 years of age, and another 20 are between 30 and 40. So all the range groups and the gender, 50, if I do 50-50, I could do a study only on women, could I? Yes, but as long as my experimental group is all women, as well as my control group is all women, I'm good. The two groups have to be comparable in these terms. Or, for instance, I don't, again, you were pointing out exercising, which could obviously affect weight loss. So both groups have to be maintained on the same routine in terms of exercising, and also, of course, the type of food that they receive, because if my control group eats McDonald's every day, and my experimental group eats healthy every day, then I'm very biased, okay? So I have to maintain also the diet of the two groups pretty similar, because I want to prove a point that my independent variable is having an effect on weight loss, okay? Otherwise, there is no way, again, if I don't control the two groups, I don't maintain the two groups comparable, that I can prove my point. And when you publish a type of result like this, and we're talking still about the cancer drug here, sorry. I do have an example about the weight loss drug, okay, which is probably easier to understand for you. But I was already talking about the weight loss. No matter what you are in front of, what you're testing, again, your experimental and control group has to be the same. If I am testing a cancer drug, my control group has to be a group of people that have the same type of cancers of my experimental group, in order to, again, see if there is a difference there in numbers of people that in which I observe remission of the cancer. Okay, if I'm measuring the size of a solid tumor, that could be the numbers that I observe. I could actually take measurements of the solid tumor and see how much it shrinks in one group versus another. And so the control group is similar to the experimental group, but it does not receive the independent variable. It receives everything equally minus the independent variable. So if I'm giving a pill, the control group is getting a pill with all the mixture of ingredients that are in the pill, because obviously when you give a drug, that drug is as a vehicle. It could be even just a little solution, but that solution, who knows, it could have some effect. So it has to be given, the mixture in which you mix your independent variable, your drug, has to be given to the control group. And in this kind of experiments, it's very important also to keep them blind, as we will see when I'll talk about the weight loss example. That is very important. So in other words, the control group doesn't need to know that they're receiving a placebo, as well as the experimental group. They don't need to know what they're receiving, because that could affect your data. Guys, you have no idea how much our positive thinking makes our brain release hormones that can have an effect on our body. It is absolutely true. It's a fact. Okay. All right. So we all agree that we have to measure in an experimental approach, measure something, find something that we can measure and collect our data. And then once the experiment is complete, we can compare the experimental group data and the control group data and come up with a conclusion, right? And compare, the word compare does not end with just looking at the final numbers. There is some other step that we have to take, and I'll tell you in a minute what I'm talking about. I just wanted to show you this experiment. This is a graph that is in my the publication. It came out after my PhD project. It lasted almost 7 years. And long story short, this experiment summarizes probably 4 years of my life. But because I was working with mice, so it already pops out to your eyes that these blue dots here, this was my experimental group. There is the data are different than my control groups. As I told you, I didn't have just one, not just two, but three control groups. Because the more control groups, especially when you are dealing with in vivo experiments with animals or with humans, the more controls you can provide, the better it is, okay? And reporting your data in a graph can be very helpful, especially to visualize. You know, if I present this graph to you, you already can tell that there is some sort of difference between the blue dots and all the others, right? And I want you to pay attention to this over here, this P. What is this P? Okay, this P is what tells you the truth. P is the truth. Okay, I'll tell you what it is in a little bit. Okay, let's move on. Now, I want to give you the example of the drugs that claims to be a weight loss drug. Okay, let's set up a scenario of what a good experiment could be to prove that this pill, this drug, is really effective to lose weight. You pull together a sample of people, and these people maybe are all overweight, okay, because of course you don't want skinny people to lose weight, otherwise you're going to kill them. So they're all overweight. You pull together a sample maybe of 100 people, and you split them in two groups that are similar. One group is going to be your control group, and the other one is going to be your experimental group. So your control group receives a placebo, your experimental group receives the drug in the same vehicle. If you're giving a pill, it's going to be the same pill. If you're giving just solution, it's going to be the same solution. And see how these people receive the drug or the placebo blindly, right? They don't know what they're receiving. Because if I think that I'm receiving a magic drug that is going to make me lose weight, my brain may produce hormones that in fact could determine a little bit of weight loss. Okay, this is proven. So you don't want people to know, especially in this kind of experiments, what they're receiving. So we say there's a blind experiment. Of course, you're going to maintain these two groups on the same kind of diet, exercise, you know, everything has to be well controlled in that regard. And both groups have to be weighed the same way. So if you decide to weigh them once a week or once every 2 weeks. You do that for both groups the same way. These are things that can vary. Nobody says that you have to weigh people every week. You can weigh people every 2 weeks. Okay, these are little things that you can decide how to do in an experiment. It's up to you. You do the process of weighing people and maintain them on the drug or the placebo for 6 months. It could be a year. Again, this is something that you decide, and you collect your data, right? Your data is going to be numbers. It's going to be the weight of people. Let's imagine this scenario. At the end of 6 months, I'm going to go out of presentation mode. I'm really curious to see what you guys say here. At the end of these 6 months, these are my results. The control group lost an average of 2 pounds per month. The experimental group lost an average of 6 pounds per month. Do you guys see my slide right now? I don't see it. Okay. Here is our, these are our results. Who thinks that the drug has effect? AJ already says the drug has no effect. Who thinks that the drug has an effect? Did you change your mind, AJ?
No, I'm sorry. I just my connection's not that great, so I had to log back in. So I totally missed the question.
It's okay. So some students say, many students say that the drug is effective. Seems like 6 versus 2, a difference of 4 pounds, they think is real. It's not just something that happened by chance. So here's the thing, guys. You're giving me an opinion, because 4 pounds to some people sound enough to say there is a difference, and to some other people they don't sound enough. So are we still basing our conclusion on opinions or on something objective?
Opinions.
We're still giving opinions, and what did we learn about opinions? They're not scientific. Is if there isn't a procedure that I can apply, a mathematical procedure that I can apply to these results, that give me a number that tells me this difference is real, I'm still giving an opinion. I can publish this data, okay? And here it comes our analysis. Whenever you collect data from an experiment, you have to run what is called a statistical analysis. Who has ever heard of this, about this? Have you ever heard about a statistical analysis to a data? I don't see your answers. In math, okay? Somebody says yes, they have learned in math, okay? This is something, when you learn it in math, I'm like, oh, what is all this? That's so boring. This standard deviation or this statistical, why do I have to do this, right? Well, if you don't do this in science, and I am the first one who hates statistical analysis, I never wanted to do them. I always went to the statistician in the department and say, here's my data, can you tell me if they're true, right? So I hate statistical analysis. I mean, I had to learn how to do them, the easier ones. You just run your data through programs. There are programs out there that do this statistical analysis, but you have to know which analysis is best fit your experiment. That's the key. All right, so we ran a statistical analysis, and the statistical analysis is set up to where it takes in consideration the number of basically the size of your data, of your sample. In this case, the number of people that have been tested. Because do you think that there is a difference if I test 5 people versus 50 versus 5,000? Is that right? Would you just test 5 people? So the size of your sample is significant in determining if your data are true or not. And so when you run your statistical analysis, you tell the program, or you put in consideration the size of your sample, which is fundamental, okay? So sometimes you won't believe it. Sometimes you have data that are very shaky. Maybe it's the difference between an experimental group and a control group is very little, but you have used thousands, a sample of thousands. You run your statistical analysis, and your statistical analysis tells you that those results are real, even if the difference is very little. So, and sometimes the difference is big between your two groups, but you have only tested very little sample, and your statistical analysis tells you that your data aren't true, okay? So you run your statistical analysis, and you're going to get a magic number, as I call it the magic number. Is going to be your p-value, which is highlighted here. Your p-value is a value that your statistical analysis is going to spit out for you, and is going to tell you if your results are really true. The difference that you're seeing is really true. And this p-value has a mathematical equation to it, which I'm far from presenting to you. Of course, I just want you to understand the concept of this p-value, okay, which is not difficult. P stands for probability. It's a probability. So it represents the probability that the results that you have got have happened by pure chance. I'm going to repeat it. P-value represents the probability that your results, the difference that you see, has happened by pure chance. So do you want your p-value to be very little, or you want it to be big in order for your experiment to be true? You want it to be as low as possible, right? That's true, because it's the probability that your results have just happened by chance, and not because there is a causative effect of your independent variable on the dependent variable, right? And so there is a cutoff that has been established by mathematicians, statisticians, all these great people, right? Our cutoff value is 0.05, okay? So let me go back in presentation mode. So once you run your statistical analysis after an experiment, you're going to be happy if your p-value is less or even equal 0.05, which means the probability that your results have been obtained by pure chance is less than 5%. Okay, so it's very little. Let's go back to my experiment. Look at my p-value. This made me jump off my chair. Do you understand why? It's very little, okay? Despite the fact that many of my mice were down here, okay? Again, when I put these results, when I saw my results, I couldn't tell anything until I ran my statistical analysis. Some, of my mice had data up here, but when I ran my p-value, that's what told me that, in fact, whatever I was doing to these mice, you don't want to know probably, it was, I was getting a true result, okay, between a true difference between my experimental group, which is the blue one, versus my other control groups. And I'm just showing the difference between, this was the most significant of my control groups. So I was showing here to my readers just that difference, the p-value relative to that difference, okay? All right, so does it make a lot of sense now? What we need to do in order to not just have an opinion of our data. Yes, we can have strong data. Even when you have something that is 10 times, say you had a weight loss in overweight people for the experiment group of 50 pounds versus 2 pounds. You still can't publish your data without running the statistical, even if it's so evident that, oh, I'm pretty sure 100% there is a difference there. If you don't run your statistical analysis, you can't publish and you're not going to be believed, okay? Because maybe you have used a different size sample or whatever, okay? So the statistical analysis is fundamental, no matter what your results are. All right, so now I want to challenge you with a very biological question, okay? Let me go out of my presentation mode because let me see who can try to help me understand what we can do here. I want to talk about something that we're going to talk about later in the course, okay, is the phenomenon of mimicry. I don't know if you have heard about this in nature. Mimicry represents the phenomenon to where one species evolves to mimic, to resemble another. And that happens mostly because the species that is being resembled is a species that predators tend to avoid. For instance, you know that the coral snake is a venomous snake. Have you ever seen coral snakes around here? I have in my backyard a couple of times. There is the eastern coral snake, which is this one on top. And then there is the scarlet king snake, which is a non-venomous snake, but doesn't it look very much like the coral snake, doesn't it? And in fact, there are many areas where these two species coexist. So basically, the scarlet king snake has evolved to resemble the venomous snake, right? And we have many examples of this in nature. For instance, the viceroy butterfly and the monarch butterfly, one of them is palatable and the other is distasteful. So basically, the palatable one, the one that predators normally would eat very willingly because it tastes really great, right? Evolves to mimic the resemblance of the distasteful one possibly in order to avoid predation, right? What would you think? So we can make an hypothesis here. We can say, well, this is what the hypothesis that actually a scientist made. He hypothesized that mimicry has evolved as an evolutionary adaptation of the species that are non-venomous or palatable to resemble the bad guys, as I call them, to reduce their chances of being predated. That's an hypothesis. I don't know if that is true. That could be something else that has pushed these species to evolve to resemble the bad guys, right? How do I answer a question like this? Does it seem that I can possibly come up with numbers to answer a question like this? Or does it seem like it's a type of question that I can't come up with any possible experimental procedure that gives me numbers? What would you guys think? Is that doable? What would you do, Drew?
It's easier for me to talk, but you could look at the rates of survival, I guess. It's or how often they get to reproduce after developing such an adaptation.
that will tell you the rates of survival. But we are asking a specific question here, or we are hypothesizing something very specific, and which is what is underlined here. The mimicry has evolved in harmless species as an evolutionary adaptation that reduces their chances of being predated. Basically, we're saying that predators that avoid the harmful species are also avoiding the harmless species. That's what we are saying, right? Do you agree in this hypothesis? So that's the point that we want to prove. If we make this hypothesis, then we have to set up an experimental procedure to prove the point, right? Honestly, I would have never come up with an experiment that Henry Bates came up with. He was genius. Let's see what he did to come up with numbers. I mean, when you look at the experiment he did, it seems very straightforward, like, oh yeah, that makes a lot of sense. But I could have never thought about it, okay, myself. So let's see what he did, Henry Bates. Before I tell you what he did, let me tell you one fact that is very important. Because based on this fact, based on this observation in nature, he could actually, that's how he came up with this experiment. There are areas, he chose the Carolina as areas to investigate on this phenomenon. And there are areas which is the unstriped ones, where the king snake is only present, so the harmless. And there are areas where the two species overlap, okay? And so keep in mind that in nature, naturally occurring areas where either you find both species together or just the king snake only, probably because it migrated away after, you know, evolving, of course, that looking like the harmful species. It probably slowly migrated away from the area here where the two species, sorry, I'm not pointing at it, but the two species overlap here, okay? And over here is where only the harmless species is present. So taking advantage of this naturally occurring difference, he set up his experiment. And his experiment was based on fake snakes. Snakes that are made of some kind of harmless rubber material. And he created an experimental group that is a group of snakes that resemble the king snake, so they're striped, colored like the king snake. His control group was just a plain brown type of snake. These are fake snakes made of some kind of harmless plastic, right? Equal numbers of these two groups were placed at field sites. Both types of field sites were 1 and 2, where you have the only harmless species present or both present together. Two groups. One is an experimental group. The other is a control group that is plain brown snakes. Put them in the fields, left them for a while. I don't remember how long he left them there. Let's see if it's written here. I don't know, for a couple of months. And then they went back to the field. They knew where they had placed all the snakes, right? Both groups. And they went to, actually 4 weeks is written here, sorry. So 1 month. Retrieve the snakes, and guess what? The snakes had bites on them, which represented the events of predation, right? Because predators were trying to eat these fake snakes. They didn't know that they were fake. So now they had something that they could count, the number of bites on the experimental as well as the control snakes. How genius is that? I would have never thought about this, to be honest, myself, okay? Now, the key point of this experiment is to compare what? Anybody can tell me what is the key point? Any ideas?
Maybe the difference between the times the brown snakes were attacked versus the other ones.
Right, that's exactly what we're doing. But in the big picture, that is what you're comparing in each experiment, right? In the big picture, what is going to tell you the answer to your question that the evolutionary, there has been an evolutionary path to evolve this kind of look in order to avoid predation, right? Remember what I told you at the beginning. He took advantage of the fact that there is a natural situation, an environmental situation in the Carolina, right? Where there is a difference. There are areas where only the harmless snake is present and areas where both species are present, right? So if the predators learn about something that is dangerous, they're going to learn it where the bad guy is present, but not where the harmless species only is present. Is that right? So if our hypothesis is true, you would see a difference of what's happening in those two different areas. Is that right? You agree with me? If you see no difference between these two areas, then it means the predators don't learn to avoid the bad guys, and therefore our hypothesis doesn't hold. Is that right? Do you agree?
Yeah.
Makes sense? All right, let's see what his results were. Next slide. Look at these results. First of all, I want you to understand this is one area and this is another area, right? So this is the number one is the area where only the harmless species is present, the scarlet king snake. And this, I'm sorry, I'm messing it up. This area is the area where, actually, I want to delete all this. It's so hard to write with my my mouse, okay? But I like when things get messy. So let's analyze what's happening here and what's happening here. First of all, first thing that pops to your eyes without even looking at the numbers. See how graphical representation is so important. What can you tell me?
The results are the complete opposite.
Very good. The complete opposite. So first of all, there is hope here, like, oh, well, there is a big difference here between the two areas. So that already tells me, right, that something is going on there. What are these results are telling me? Wherever the coral snake, the bad guy, is absent, who is getting more hits?
The fake coral snake. Or
fake
the
coral snake.
artificial king snake.
Yeah. The striped one, right? Whereas in the areas where the bad guys are present, who's getting more hits?
The brown artificial
right?
snake.
Now, tell me that this is a striking result because these results tell you that in a normal situation, the king snake is the one that would get more hit. But why? Why isn't this equal? Why isn't this, are these two equal? It's a very easy answer. You don't have to think through too much.
It's because the artificial king snake's brighter, right? It's more visible.
Oh. Okay, very simple, right? Of course, a predator is going to spot it more easily. So that makes your results here even more significant, because these results tell you that in a normal situation, in fact, the king snake is the one that is more visible and it gets more predated. Now, the fact that in the area where the coral snake is present, you have such low predation rate, it really reinforces the idea that the predators are purposely avoiding this one. They see it very well, they see it more, but they avoid it. And that is told you by this graph, okay? So how genius was all that, okay, to set up this experiment, and these results really prove the point, okay? So I wanted to give you an idea of how even very biological questions, you know, if you use a little bit of imagination, you can answer them. You can come up with experimental procedure that gives you numbers that prove you the point. And again, only numbers can prove a point, nothing else. Okay, so obviously I'm not showing you the statistical analysis here, but I'll tell you they are very significant. Okay, so here I wanted to show you how we approach biological questions. Now, how are we doing with time? Yeah, just a few minutes. I just wanted to define hypothesis versus theory. We pretty much already defined hypothesis. Remember, hypothesis is a tentative statement. It's very preliminary, most likely subject to change. That's very different from a scientific theory. A scientific theory generally consists of many hypotheses that have been holding for a long time, and they're pinnacles of science, and they're widely accepted by the scientific community, and they withstand for a long time. Basically, never proven wrong, because if a theory is proven wrong, it's not going to be a pinnacle of science anymore. This doesn't mean that scientific theories can evolve. One good example of is Newton's theory of gravity, which it was a good theory, but it was not the 100% truth. All the mathematical equations that Newton came up with are true. They're applicable on Earth, but they're not comprehensive of what happens in the universe. So, you know, Einstein evolved that theory, okay, and evolved the theory in a more comprehensive one, okay? So theories are the highest level confidence of understanding of the natural world that we have, okay? And there are theories that we're gonna look at this semester. One is Darwin's theory of evolution. We're gonna talk about that extensively this semester. And one thing that we're going to learn is that especially the theory of evolution is kind of impossible to prove, okay? There are some few experiments you can do, but with some particular organisms, but you cannot prove the theory of evolution, modern theory of evolution, with an experimental procedure that involves complex organisms. So what we base our theory of evolution is on evidence. There is a lot of evidence that support it, okay? But again, Darwin's theory of evolution has never been disproven, and so we accept it as true. And why do we care about all this? You know what, guys, there is no better example right now. I used to give an example of viruses in my classes before COVID-19. This slide, I made it like 3 years ago. I still use it. But knowing how organisms evolve, and evolution is change. Change happens in genetic material, and viruses have genetic material. How they change, how they evolve, it can help us predict where this virus is going, and are there going to be variants that we have to worry about, things like that. The theory of evolution helps us make prediction, and this is very important, right, for our health. And so here, what I'm trying to tell you is that the theory of evolution has a lot to do with also the approach that we take in medicine, in health, is not disconnected from it. It's not something abstract. Okay. And so I'm done. I'm just on time. Okay. I hope you guys enjoyed this lecture. Are there any questions that you have? Oh. Have you guys heard me for the past 5 minutes or what?
Yeah, we can all hear.
Could you see the slide as well?
Yes, ma'am. It's been working the whole time.
Okay, so there was some, maybe it was your internet. It was, let's see. So just want to summarize and tell you that for this lecture, what's important to really remember is the scientific process, the various steps. And again, if you apply a logical procedure, you know the steps, you would recognize what the steps are to take in a scientific process, the difference between theory and hypothesis, and how we control experiments, and statistical analysis that we learned today. If we don't do that, it's still an opinion, right? And we cannot rely on that. All right? Holly cannot hear me. Let's respond to her. Oh. Students. All right, guys, I'm done here. If there are no questions, I guess I'll see you on Tuesday. All right?
Thank you. Have a great weekend.
You too.
Thanks for the
Thank you.
lecture.
No problem. Have a great day and the rest of your week.
I think Rachel had a question in the chat.
To know if the kids. Okay, Rachel, sorry, I didn't see your question so far. She says, I'm going to, if the king snake and coral snake live in areas together, why not measure the bite marks between those two? You mean the real ones or the fake snakes? Are you there, Rachel? Rachel?
She said the real ones in the chat.
You mean the real ones? Well, you could do that, but the key point, let me go back to the slide, is that if you don't have, first of all, when these snakes are predated, they're probably going to die. They're going to be, because the fact that you only see the marks, the bite marks on the fake ones is because, you know, they're left after that. The predator learns that it's not, it bites into it, but it walks away because it's not plastic, it's not. So the real ones will be gone, will be dead and gone. There is no way you can come up with numbers, I don't think, in nature doing this experiment on the real snakes, because they're not just going to have a bite, they're going to be eaten out by the predators. The reason why the predator eats them out, it wants food, right? So bites them out because it wants to use them for food. So I'm sure you could do that in actual nature. Does that answer your question?
Hi, can you hear me?
Yes.
Okay, awesome. Sorry. I was kind of confused on the experiment. Like, why did they use brown snakes instead of like using both replications of the coral snake and the king snake? Wouldn't that be more like efficient and effective?
See, the use of the brown snakes tells you something very important here. Let me highlight here the slide. If you hadn't used brown snakes, you wouldn't have these result. This result tells you that in a situation where there is a choice where there is the same number of snakes out there, but half of them are striped and another equal number is not striped, the ones that are more predated are the striped ones. Do you agree?
Yeah.
In a neutral situation, because they're more visible, right? So it's important to, I think it was important to use the brown snakes to prove the point, to reinforce these results. Because the second set of graph here tells you that there is a real avoidance. Is even more reinforced by the fact that in a normal situation, these are the snakes that would be more predated because they're more visible.
Okay.
Yes, I understand what you're saying. The difference between this and this would have already told you that, in fact, in these areas, in this area where the coral is the bad guy is absent, in fact, those are the snakes that are more predated. And I totally agree with you. But having a control there, it makes your results strikingly significant in that regard.
Okay.
Because
I
now,
gotcha.
okay. So
Awesome. Thank you so much. Sorry, I
no,
had to ask
that's
a question.
absolutely fine. Absolutely. I love these kind of questions, okay, to clarify.
Well, thank you
All
for
right.
explaining it to me.
No problem.
Have a good day.
You too. You guys have a good one. I'm gonna stop the recording.